In this video, we're going to talk about tangent planes, which is the multivariable generalization of a tangent line that we saw in single variable calculus. We're going to figure out how do we define a tangent plane, how do we compute a tangent plane. So in this example, I have the graph of a function, and I've specified a particular point in red, which is a spot on the graph of my function in x0, y0, and it has a height z0. And then what the tangent plane is some plane that's going to go through that point that just comes along and sort of kisses the graph of this function at that particular point. And nearby, it's a close value. The tangent plane is a good approximation for the graph of the function. I can have a tangent plane at this spot, but I could move it around out the front, and at a different location, I'd get a different tangent plane. I could even talk about the tangent plane at the spot that's right on the top here. At that top, the tangent plane is parallel to the xy plane, kind of analogously to when you would take a derivative equal to 0 and have a horizontal tangent line in single variable calculus. So, how do we find these? Well, let's begin with the goal. A loose sense of my goal is I am looking for some plane. I'm asking two things. I'm first asking that the tangent plane and the graph of my function, that they meet at the specific point x0, y0, and z0. And then secondly, I'm asking that nearby that point, that the tangent plane is close in some sense. It's close to the graph of the function, but what exactly I mean by that, let's put a pin in it, and we're going to come back to it later. Now, tangent planes, well, it's a plane, and let's talk about the formula for a plane in general. We've seen this before in our multivariable calculus course. One way to give the equation of the plane is as the dot product between the normal vector and a generic vector that lies in the plane, the vector that emanates from a point P0 out to P, and that this dot product is asserted to be 0. The way we came up with this is we had a picture, we had a plane, you had a normal vector end of the plane, it came out of a particular point, x0, y0, z0 on the plane, and then indeed we demanded that if this normal was truly going to be normal, it had to have a 0 dot product with any vector that lay in the plane. From this particular equation that we have, we can expand it. If we give the normal vector the components a, b, and c, then we're going to get the formula a times x minus x0, plus b times y minus y0, and c times z minus z0, and that the sum of all these three things is 0. So if I'm asking the question, how do I find a tangent plane at a particular point? Well, the point is easy to figure out. The x0, y0, and z0 that you're asked to find the tangent plane at, just plug them into the formula. The harder part is the a, the b, and the c. How do we come up with this normal vector to the graph of the function, which will give us the normal vector to the plane? I'm going to begin with a simplifying assumption. Imagine that c is any non-zero number. If that was the case, like it was, say, plus 7, I could divide through so that the coefficient of the z minus the z0 was just equal to the value of minus 1. This always works unless it's c equal to 0, and I'm going to let you pause and think about why that is not relevant if I'm asking for a tangent plane to a differentiable function. Nevertheless, if I make this simplifying assumption that's equal to minus 1, then I can clean up my formula a little bit. I get the same a, x minus x0, and b, y minus y0, but then I say plus z0 equals z. So what this is, well, a linear function. It's z, the height of this function, depends on the x and y, and it depends on xy in a linear way. The value of x is raised only to the power of 1 with multiplicative constants out the front. One way to think about tangent lines back in the day and tangent planes today is that what we are trying to come up with is an approximation for our nonlinear function. We approximate that nonlinear tricky thing with a linear thing that is much more simple to understand. Indeed, this is the linear thing we're going to approximate. We just have to figure out the a and the b. So how do we do that? Remember, our condition is we want the a and the b to be close, nearby, in some sense that we haven't yet specified. Well, let's take that formula. And let me plug in first the value y equal to y0. So I plug the number in, and the second term goes away, and I'm just left with a times x minus x0 plus z0 equal to z. This is like me taking my surface, and I'm going to just restrict to the plane where y is equal to y0. That's going to cut through my surface, and notice what this equation is. That is the equation of a line. So if you imagine the height of your function z only depending on x, which it would only if you had plugged in a specified y value, You have a z depending on x. And indeed, in single variable calculus, we asked and answered the problem of how do you come up with a good approximation line, a tangent line to the graph of a function of a single variable. Well, this is the equation of a generic line. The answer in single variable calculus was the a was just the derivative. It was the derivative at the point we're talking about. So in this case, we are focusing in on a single variable function when you specify that y is equal to y naught. And so we get the same answer, that a, if it's going to be a linear approximation, has to just be, well, the derivative of your function. In this case, the only variable around that we're taking a derivative is with respect to x. So it's the partial of f with respect to x when you plugged in the y naught. And then you evaluate this at the particular point x naught. This is indeed what single variable calculus would give us to the special single variable function f of x and y naught. Likewise, let's go and plug in x equal to x naught. That gives a different linear equation, b times y minus y naught plus z naught equal to z. Again, I have a single variable function. The z now is only depending on y. And the question about how do we find a linear approximation to that single variable question was asked and answered in single variable calculus. The answer was you made the slope of the line the derivative. In this case, it's the derivative with respect to y now. So the linear approximation will be a linear approximation when b is equal to the partial derivative of f now with respect to y at the value of x naught, y naught. So there we have it. We have inherited the notion of a good approximation from single variable calculus to determine the a and the b that we need in multivariable calculus. Put it all together, I can get the equation that the partial derivative with respect to x at our point times x minus x naught plus the partial derivative with respect to y at our point x naught, y naught times the y minus y naught plus the z naught is equal to z. Now, if I want to sort of interpret what's going on here geometrically, let me put up the tangent plane and the graph of my function. And what I've done here is that the yellow curve and the yellow line represent me slicing at a fixed value of y naught. I plug in the y naught and I get this yellow curve here. And the tangent line to that yellow curve, well, the tangent line lives inside of the tangent plane. If you come along and cut the function, you come along and cut the plane as well, and you get a tangent line when you're focusing in on y to y naught. Likewise, if you specify that x is equal to x naught on the original graph of the function, that turns into this blue curve. And then the tangent line to that blue curve lives within the tangent plane at the particular point. Nevertheless, we get this formula. So let's see how it works out in a specific example. In the example I'm going to use is the one that I've been programming here, is the function is 2 minus x squared minus y squared. And I've specified a particular point. The point x naught is 1/2 and y naught is 1/2. That's what we're going to investigate. So the first thing I'm going to figure out is maybe my z naught. So what is the height of the function at this particular point? Well, I just plug it in. What is f of 1/2, 1/2? I plug it in and I get the value 3/2. Then I want to figure out the partial with respect to x and the partial with respect to y. Well, the partial with respect to x here, this is going to be the same thing as minus 2x. But I evaluated the point x equal to x naught, so it's minus 2 times 1/2 or minus 1. Likewise, if I take the partial with respect to y here, this is minus 2y. I evaluate at y naught equal to 1/2, and I get the value of minus 1. Take those 3 points, plug it in, and finally I get the formula z is equal to 3/2 minus x minus 1/2 minus y minus 1/2. And that's my equation for the tangent plane.